Okay, let's get started. So we are continuing our discussion, which should have been on Thursday, but obviously the weather canceled things. So here is the continuation of our torque versus speed characteristics, which you actually got to see a little bit of that in lab. And we were only actually able to see the motor application of the torque versus speed characteristic. But if you're capable of driving it faster than synchronous speed, well, the concept of your stator field still rotates at synchronous speed, but now you're pushing the shaft faster than what it's supposed to do. So what ends up happening is you still have that rotating magnetic field that's induced, but now it's trying to go and trying to slow things down. So now your frequency is in the opposite direction. So instead of making up the difference between actual speed and synchronous speed, it actually is going in the opposite direction. And when it goes in the opposite direction, now it's inducing a current into the stator windings. So no longer do you have a motor, you actually have a generator. So as we talked about in class a number of times, any AC machine can operate as a motor or a generator. It just depends on the application and torque. In the synchronous motor, it has to run at synchronous speed. So whatever we're driving it at, that's whatever output frequency it's going to be. Over here, will you get an output frequency? Not really, because what do you need? You still need some sort of output voltage, if you will, that's going to give you that 60 hertz. So in an AC induction machine, you can spin it all you want, but until you have a voltage connected to it, some sort of a power source, it's just you're just rotating something in a set of windings that's not doing anything. Remember, you need two magnetic fields, stator and rotor. And when you force rotate it, you don't have any magnetic field. You're just physically rotating it. You still need to get that changing magnetic field. And how do you get that is you've got a voltage that is providing the magnetic field on the stator circuit, which then induces the rotor circuit. It gets you the one that's on the rotor circuit. So here's the biggest difference on stator synchronous machines versus induction machines. Synchronous machines can support a grid. They can run independently from the grid and they can feed the grid. AC induction machines cannot do that. You have to have some sort of voltage reference so that they can provide power. So another reason why you don't see very many induction generators is they don't do anything unless you have voltage. So remember we talked a little bit about wind turbines way back when? So wind turbines use doubly fed induction generators. They use an induction generator, but you actually provide an AC voltage on the rotor circuit to kind of add or subtract. So it's not a true induction machine. That's why it's called a doubly fed induction machine. But the reason why that's able to work is because they're interconnected to the grid. So that's the only way a wind turbine works, is actually interconnected to a grid that is energized. Now, that's also a problem because one of the things that happens during regular operation of a system is you get faults. And if you get a fault nearby a wind turbine, what happens? The voltage collapses. And now the wind turbine, which was helping to support the grid by providing some power, now it's no longer able to provide any of that power, right? Because the voltage is really low, so it's not able to get enough magnetic energy to be able to create this magnetic field. So the doubly fed induction generators for many years were really adding to, if a fault occurred, it actually exacerbated the fault, because when the fault happens, you get a lot of current and then the voltage tanks. Now your doubly fed induction generators, all the wind turbines, they're not contributing anything. So the voltage drops even further and then your fault current drops. And so what you had is a very unreliable system. So if you look at more of the wind turbine facilities now, they have to have the capability of providing voltage. It's called low voltage ride through. They have to provide voltage support for, I can't remember if it's 1 second or 10 seconds, but it's a fairly long period of time. And there's two ways to do that. The first way is they call dynamic bar compensation. It's basically a bunch of capacitors. They can switch things on and off. Another way that they do it, and some of the bigger projects do it, is they use a synchronous motor. Synchronous motor can sit there, right? And it can provide whatever voltage you need. And once it's up and running, as long as it has enough inertia, it actually will start to slow down, but it's able to keep the voltage up because, again, it's a synchronous machine. It doesn't need voltage support. It provides its own voltage support. So as that synchronous machine is spinning down, it's able to keep the grid voltage up. Okay. So you'll actually see some of the wind projects in Western Maine actually use synchronous condensers to go ahead and provide voltage support. So just a couple of things over here. You'll look at the motor operation. You see the input power is electrical. The output power is rotor, P on the rotor, so mechanical equivalent. And then you're actually converting that to mechanical power. And then it shows you a few losses here, right? You can actually see you've got the stator copper losses, core losses, you have rotor copper losses, and then you have friction and windage. That's what the V stands for, it's velocity. And then all your output power is mechanical. Over here, the power is opposite. The input power is mechanical. Now you have some rotor and friction and windage losses. Now you moved on to the stator, so you got some core and some stator copper losses, and then this is electrical output. You'll notice that this speed goes all the way from 0 all the way up to twice synchronous speed. And what happens at twice synchronous speed? I'm not exactly sure. I don't know if it would continue to operate because now you've got to more than double the speed. So I don't know if even the frequencies would exist or even work well. So this is motor generator. One thing I'll say is both of these, if you look at rotation, they're both rotating. And if you're facing the shaft, they're operating in a clockwise direction. Look at the speed. The speed is also in a clockwise direction, but look at the torque. The torque here, it's shown, it's a little hard to tell, but this would be the equivalent torque that is the equivalent for the electrical power. So our electrical power is driving a torque that's in the same direction as the speed, which makes sense. It's a motor. That's where the power is going in. So it has to rotate the shaft. Over here, the torque is in the opposite direction. Does that make any sense? It's a generator, but does that make sense that the torque's in the opposite direction? Think so?
Would it be decelerating?
Would it be decelerating? Well, keep in mind, we want this to keep generating power. So what decelerates is the whatever is driving the machine. So it could decelerate, but it's decelerating whatever's driving the machine.
Is the electrical field moving the other way, giving it a resistance to push up against, and that's what giving it torque?
It's not really the electric field going the opposite direction, but you're absolutely right. It's the induced torque. So when I steal electrical power out, that has to act like an equivalent torque, right? It's power. Power equals torque times omega. So I'm taking electrical power out. That means I have to take some torque and remove that. And if I'm driving it externally in a clockwise direction, my mechanical power has to be going in a clockwise or counterclockwise direction because that power is going out. And if they were both going in the same direction, the unit would continue to speed up. This is an induced torque. This has to be in the opposite direction to counterbalance the applied torque from the mechanical shaft. So induced torque is always in the opposite direction of the applied torque. Otherwise, it will just continue to speed up. All right, max torque. We already talked about max power transfer, the last class we were actually in person. So max torque occurs when the power transferred to that R2 over S is at a maximum. Remember that rotor circuit? That's the max power. Question?
Yeah, so this is an induced motor, right? What we just saw right now.
It's an induction motor, yeah.
Yeah. So does it also work as a derivative too?
Yeah, that's what this first slide shows. It can go in either direction.
So does it still work as a, even if the rotor is the cage, no?
Does it still work as a motor? Is that what you said?
As a generator, even if the rotor is the cage.
Doesn't matter if it's a cage or not. It still works as a motor or generator.
But it doesn't, technically, it shouldn't. I mean, I don't
Why wouldn't it? All you need is two magnetic fields, right?
But then there's no, I mean, in a sense that if the other one, the operation, you put a DC board.
For a synchronous machine has a DC, right, on the field.
Yeah, which create
The magnetic field, yeah.
Which makes sense. But now, since there's a cage, there's no magnetic field.
Sure there is. Don't you have a current that's induced because it's a current is a closed set of windings or a loop is in a set of magnetic field and they're seeing a changing magnetic field.
But where does the magnetic field come?
Magnetic field comes from the stator. Remember, you got a voltage there. So you got the current that goes out And then you've got that current flow that's going to give you a magnetic field.
We're thinking about the generator, right?
Yeah, you still need, so remember what we said on an induction machine, your voltage has to be externally supplied. If you don't have any external voltage, then you're right, you can never get the system started.
Yes.
But you have that external voltage so that you get that magnetic field on the stator and on the rotor. Once those two exist, then you spin it and now you got a voltage. So you need that voltage to provide the magnetic field to do that. That's Eli the ice, right? You need a voltage there to be able to provide the magnetic field. So an induction machine always will operate at a lagging power factor, whether it's a generator or a motor.
Which means to start an induction machine as a generator, I need to put the voltage.
It won't run otherwise, correct? Yep.
And
You can get it spinning, but it's not going to actually create voltage until, create any output power, convert any power to electrical power until you have a voltage on the output.
I need an external voltage first.
First and always, because the moment you pull the voltage away, that magnetic field no longer is available because your voltage is what's providing the magnetic field that you get induced in the rotor. It can't provide it itself.
But the synchronous motor, when you run the generator, you don't need that because.
If it's synchronous, you don't need it because it provides its own. Yep.
Okay.
Yep. And that's what we were saying. So a synchronous machine can run the grid without any support. An induction machine needs some support.
Oh.
All right, so max power transfer, R2 over S. So we're going to set, if you remember max power transfer, it's when the load impedance matches the source impedance. So now we do things in terms of magnitudes. So we're going to set R2 over to our maximum torque slip value and just use our magnitude calculation using the hypotenuse. And now we'll solve for our torque where that occurs. We can just use our calculation here. Once we know what the slip occurs, we can plug that into our torque equation. And here's how we calculate max torque. Again, this is an approximation. This is not exact, but this works really well to giving you a close number. One thing to note, if you look, the slip at maximum torque is directly proportional to the rotor resistance. You can see slip is equal to R2 in the numerator, right? So if you tweak R2, you can actually change your value of slip. And so that's what designers do. If you need to move the characteristic of when the max torque occurs, you can increase or decrease R2 to change that torque versus speed characteristic. It's always going to look kind of like this, having a peak value, but I can move the peak to the left. Probably can't move it much to the right, but I can continue to move it left so that I can move it all the way so that max torque occurs at startup. And we'll learn more about what are called NEMA design categories for induction machines as we get further and further along. But one thing to say, so I move the torque, but if you notice, where's R2 in here? So our slip max is directly proportional to R2, but the max torque doesn't care about R2. So I can tweak R2, change that speed where that max torque occurs, but the max torque is still going to be the same value. So remember at the beginning of class, we talked about two types of circuits on the rotor, the squirrel cage or the wound rotor. This is what we used to do back in the day when we didn't have adjustable frequency drives. We actually had a wound rotor machine that you would monkey with the resistance. You literally would add or subtract resistance in the rotor circuit to change the speed characteristic. And that's the only way that you could actually do speed control back in the day. That's this wound rotor design. So here are the different characteristics. You can see R1 is the most common one that we would see. That's called a NEMA design B. Then we start moving to the left until you get to all the way to an R6, which means you're going to have maximum torque occurring at startup. Anybody want to guess as to why we go with the NEMA design B, the R1 here? They all have the same peak torque, right? So there's no advantage to doing it The current, say more.
Like,
Pardon?
pay.
Say that again?
Pay less.
Pay less current?
No. Because if they use less resistance, maybe use less current. And maybe
So if you inject resistance in there, obviously you're gonna have more I squared R losses, right? Any other reason? Well, what if you need a fair amount of torque? So in some cases you need it, but I don't know if it would necessarily mean more wear. It might be more mechanical. The mechanical system is screwed up. But why would you want to run on R1 instead of R6? We already talked a little bit about, we don't want to add more resistors in there, that wastes energy, but sometimes we need to. Any other reason?
I'm guessing you want to have access to more torque at your normal operating speed, right? Where
No, because we're going to be all the way down here, right? So we don't want more torque. We're way down on that point of the curve. Any other guesses?
maybe when you want to start with less torque, you start with less torque and then you.
Well, ideally, if I could, I would make sure this is flat the entire way to here and then cut down, right? If I have more torque available to me, what does that mean? Nobody here's a lead foot. When your car's got a lot of torque, when you have your max power at no speed, you take off and you get up to speed really quickly, as opposed to having to wait till your engine gets to 4,000 or 5,000 RPM, whatever it is, to get all that torque. Wouldn't you want it to be a perfectly flat until you were kind of, reaching your threshold? So more torque means the load starts faster. It's ready to accept, it's got up to speed at a faster rate. So it ideally would be this if we could. But there's one reason you're all forgetting, yes.
Because you want it started off with a little bit less torque so it doesn't slip while starting.
What do you mean slip? What would slip?
Oh, the pole.
Remember, you're driving a mechanical load. So you're saying the belts would slip?
Depending on how you drive.
It's possible, but I would imagine most of the time you're using a three-phase induction motor. It's a solid connection. There's a keyway that you're just bolted together, and that's typically what you've seen, because a belt, if you're putting out 500 horsepower, all that power going through a leather or rubber belt, don't last very long, right? So when does maximum efficiency for an induction motor occur? When there's no slip. We said the most efficient applications are when we have very, very little slip. So if you need to put out, let's say a value of power that's equivalent to right here, right? That's the power. The slip here is way less than the slip over here, isn't it? So running it at an even design V by default means you're a more efficient machine because you're running closer to synchronous speed than any of these other designs. So in addition to R2 using up energy, also just the operation of the motor itself, you get higher rotor copper losses just in the built-in resistor or the equivalent resistor for the rotor circuit without running anything different. So more efficient means running it at this one as possible, running that as much as possible. All right, let's do an example. We'll do 50 hertz land. So 2-pole, 50 hertz. Motor supplies 15 kilowatts. That's mechanical equivalent power to a load that runs at 2950 RPM. What's the motor slip is the first question. How would you solve for the motor slip? Yes, sir. Yep. So what do you need? What's missing in that equation? We need the synchronous speed, right? We need N sub S to be able to do that. So the first part of the problem is how do we get N sub S?
120. 50 divided by 2.
Right, then because we need a number of pole pairs. So at this point, we need this piece of information and this piece of information and this piece of information to be able to calculate what the slip is. The other part is based on 15 kilowatts. And then this one where we start to get a little bit tricky, where we say, what will the operating speed of the motor be if the torque is double? So let's do the first two parts based on what information we have, and then we'll move to 3 and 4. All right, so here's the equation that B mentioned. Sync speed, 120, electrical frequency divided by the number of poles. So 3,000 RPM is what that rotating magnetic field on the stator rotates at. So our slip, NS minus NM divided by NS is 1.67%. Now, oops, is this working? We don't have any real losses, so we're going to assume all our converted power is our load power. We don't have friction windage, so we'll just assume everything's there. So power equals torque times omega. We used that equation a lot yesterday. Let's continue on. T induced is your watts divided by your omega sub n. Again, convert your radians per second, convert RPM to radians per second. And this is the actual operating speed, 2950 RPM, not synchronous speed. So we're just under 50 Newton meters of work. All right, so what happens in that case where we double the torque? Well, we have to kind of go back to the curve. And what we're seeing is, and this is a bit of an approximation. So what we're going to assume is that this is a very linear area. And we're going to assume that the slope of this line is essentially a 1-to-1 ratio. So if you double the torque, you're going to double the slip. Okay? You double the torque, you double the slip. Once you start getting past this nonlinear operation, all bets are off, right? We can't necessarily do that. So part 3 is double the torque, just double the slip. That's all you need to do. Nothing more complicated than that. Now we know what our new speed is because we can calculate N sub n. We know what sync speed. Sync speed doesn't change. We just use our new value of slip. We get 2,900 RPM. Now our converted power is going to be doubling of the torque. So we have 48.6 Newton meters times 2. Okay. Now we have to convert that to our value here, and we need 29.5 kilowatts is what we actually do. You will notice that the power, right, before it was providing 15 kilowatts of equivalent. If you double the torque, wouldn't you expect to provide 30 kilowatts? But you are not, because you got a speed change as well, right? So just because we double the torque does not mean we double the amount of power output. So we would be 30 kilowatts if that was the case.
The power went down.
Slightly because of speed reduced. Yep. Yep. All right, let's do some problems with some equivalent circuits. 460 volt, 25 horsepower, 60 hertz, 4-pole, Y-connected, wound rotor induction motor has the following stator impedances, all reflected to the stator side. We've got a bunch of stuff to do. Very first thing, and hopefully this has been clear already, that's irrelevant. 25 horsepower means nothing to me. Why does it mean nothing to me? Because that's just a rating on the motor. It doesn't tell me anything about how this particular machine operates. I just need to go ahead and make sure I get the understanding. What I really care about is 460, because I need to know what voltage applied is. 60 hertz. Why do I need to know 60 hertz? Synchronous speed. And the 4-pole is important. Y connected is awfully important to me. And the impedances. So let's do. All I need is this, and let's bring up whiteboard and paste this in. Oops. Okay. All right, so why did I paste this in? Because I'm going to draw the equivalent circuit. People, it seems like in this class have had a little bit of a difficulty of trying to, figure out how the concepts we're talking about in class relate and why I'm able to go through this so quickly. Because when I see this description, I immediately think, what does the equivalent circuit look like? So I'm going to actually start building my equivalent circuit. I've got a resistor. I've got an inductor. There's an inductor over here, and I'm not going to include a core resistor because I don't have any information on it. So this is 0.641. This is J 1.106. This is J 26.3. Now I'm on my rotor equivalent circuit. So everything has been converted to the secondary side of the the primary side of the transformer. And now I have my J.464. And the last thing I'll have over here is my two resistors. This one will be my R2, 0.332. And this is 0.332 times 1 minus S over S. That's a variable resistor. Okay. This is and technically I should have put these in reverse order. So let's just erase this just to make it easier. All right, and the reason why I swapped that around is because this is going to give me output power. I want to include all the losses of the circuit before I got to the output, so I put them over there. I can combine these two, if necessary, to be R2 over S. Last thing I need to do to finish this off, let's put my voltage source. What's my voltage again? Yeah, remember it's Y connected, so it's 460 over the square root of 3. Don't forget magnitude and angle at an angle of 0. Okay, so now it's just equivalent circuit. So you can do those concepts of the Thevenin equivalence, or you can do I1 and I2 and do the loop equations approach that we did a couple of classes ago. Either one works. So this is the approach to do it with the Thevenin equivalent. You just have more equations to remember. So when I plug all those in, I got 255.2 volts for my V Thevenin. My R Thevenin is approximately 0.59, and my X Thevenin is 1.16. To find max torque, all I need to do is plug those numbers in, and I get 229 Newton meters. The torque when that occurs, or the slip when that occurs, have to memorize these equations, and I get 0.198. So a slip of almost 20%. Where this occurs is 1444 RPM. Where, if you remember in lab yesterday, what was the most people could get without it crashing? 280, 1280, 1290. So not that far from a typical number. Now we can find the starting torque. Remember, the starting torque means that things not operating. So we have a slip of 1. So in our equation for torque, we just let S equal 1, and we have this value over here, 104 Newton meters. Rotor resistance is double, then the slip and maximum torque doubles because, oops, I have a typo here. It's not 2, it's 2. No, that's correct. Doubles as, why did I just say doubles as well? Because it is 2, it is spelled correctly, but. So my slip has doubled. Now my speed is 1087. Maximum torque does not change. As long as I don't increase my rotor resistance so much that I limit the amount of current, then I can do that all day. Because it's a wound rotor, I can inject more resistance into the rotor. Starting torque, though, does change because I've moved my max torque back a little bit. I'm not going quite as far down, so I'm actually further up on the curve. So instead of the 104 or whatever it is, now I'm getting 170. How about some MATLAB stuff? No? This is the other way to do it. And I think it's easier, and we'll check our results. So here is MATLAB. Here's the script file I wrote. So please tell me if I entered any of these values incorrectly. 0.641, 0.332, 1.106, 0.464, 26.3. My voltage is 4.6. Yes. I don't think so. If you'll be able to see on the video after the fact, and if anybody wants the MATLAB script, I can post it to the class folder if you want or not. It's up to you. But is it really that hard? There's lots of comfortable seats up front if you'd like to move up front. But I'll make it available after so you can see it that way. And usually the definition on the videos and the process is HD, I think what YouTube does. So they're generally pretty easy to see, right? So yeah, I don't think I can make this bigger. I'm not sure. MATLAB is not a fancy, it's not a graphics package where, it just does calculations. Here's my voltage, 460 divided by square root of 3 at an angle of 0. 4-pole machine, my frequency is 60 hertz. What's the first thing I do? I calculate synchronous speed using our equation. Then I calculate n sub s, which is if I need to know things in RPM or radians per second, I can do the calculation. Now I did the Thevenin equivalent approach. This is just using Thevenin equivalents. So the V Thevenin approach, R Thevenin, X Thevenin, T max, slip max, and then my pullout torque, that's actually when, and if you remember from lab, that's when maximum torque occurs. Pullout, breakdown, whatever you want to call it. So I'm going to run everything to here. Let's hide this and run this. And I'll do one step. And MATLAB is here. All right, so all these equations or all these results should match pretty closely to what we did in the slides. Again, it's not perfect because when you enter things in MATLAB, you can enter things with a lot of precision. Remember on the slides, it's 255 point whatever. And so when you do it in your calculator, it's not going to be as accurate as just keeping it all in MATLAB. But they should be pretty darn close to what we have. Okay, so this is just doing the Thevenin equivalent approach. But if you recall, the nice thing about MATLAB is we can do the loop equations pretty easy, and we can do thousands of loop equations. We can get our own curve. We can build our own torque versus speed characteristic curve, and we can actually pull the points off the plot. So that's what we did here. That's what the last time we did a class. I'm going to do the same thing here, and I'm going to run through this, and I'm going to plot it and see how closely it compares to those values. So I'm going to stop this, and I'm going to clear that breakpoint. And then I'm going to run to here. Now I'll plot it. And let's see. I said max torque is around 228. .231 is what MATLAB is saying. And if you look at the speed, 1,432, what did we calculate on the slides? Do you recall? .1444 RPM. So doing the Thevenin equivalent approach is pretty accurate, but not, as accurate as MATLAB. So you can see that I can do that here. So 1444 versus 1438 seems close enough for me. If you also look at what I did in MATLAB, so this is just if you want to get cute with it, you can actually have MATLAB pull a specific point. So if you don't want to look in the graph, you can actually have this index feature where it's going to go in and find the max torque and pull out the max slip value. So we'll run through that. And then we'll see that our max torque, and I don't really care about the index, that's just where it is in the matrix. but our max torque was 230.8 versus the 228. And that slip speed occurred at 1437. Okay, so you can see it's 227.8 versus what we did a more exacting approach. We got 230.1 or 0.8. Max torque occurred at 0.1979, where we calculated it at 20.14. And then the speed difference you can see is 1444 versus 1443 or 1438. 1,438 versus 1,400. I don't know, these are about the same. So yeah, they're pretty close to being the same. This is 443.7 and this is 443.8. So pretty darn close. Now let's double the value. So if you remember from the PowerPoints, we had to double the torque, which means we double the resistance. All it does is we just assume that the slip changes by the same ratio. So it doubles up and then the speed is. How about we change that over here? Now I'll clear all my breakpoints and run it. And now look at the curve. So it's starting to look more and more from the PowerPoint. Starting to look more like this, right? Before it had more of this shape. Now we've doubled the rotor resistance and we look more like that. What's happened here? We're still getting around 231 for our max torque, but look at the speed. Instead of 1438, it's now at 1069, but the torque hasn't changed. So our approximation is pretty good. And we can continue to monkey with it, where we can change this to, let's quadruple our resistance. And let's go back to our plot. Now this is looking like almost all the starting torque is at the beginning. Which, again, if you have a lot of mechanical load initially, you might need to run an application like this. But you'll also remember where our power here is outputting the, the full load, the equivalent of 25 horsepower. Now, instead of being at 1780, now you're at 1728. So you're going to have a less efficient operation. So that's what the wound rotor stuff does for us. It actually allows us to change the characteristics. So 5 times the resistance looks like we get all the starting torque right here. Remember we said 231? What happens if we go to 10 times? Straight line? Take a look. Becoming a straight line, but now look what we've done. Our torque that was able to put out, that motor that was able to put out 231, now can only put out 194. So we put too much resistance in. Now we've defeated the capability of the machine. It can't put out as much torque. It can still do it. It can still operate, but it's not nearly putting out as much torque. So this is when we've overdone it. We've actually decreased the ability of the machine to support load. So going up to 5 times, you can change the characteristic, but after that, you can't do much more than that. And if we made it smaller, let's say, so multiply it by, let's say 0.5, let's have the resistance. Whoops, sorry about that. Multiply it by 0.5 or 1/2. Now look how steep it gets. So still 231 is the peak value, but look how steep it comes down. So this would be the best application if you're trying to maximize efficiency. But now look at my starting torque. It's way reduced, right? If you compare it to 1/2 to 1, it's almost double what the starting torque was. So this is why we kind of picked, or the NEMA, which is a National Electrical Manufacturers Association, I think, they kind of come up with the standard for motors and generators. They actually have a standard called MG1, which has a lot of the details. But they actually come up with NEMA Design B is like the most, it's the best design for overall applications. So if you do an edge search, and let's look for, let's do a 250 horsepower three-phase motor, but we don't have to, we already know it's 460 volt motor nameplate. Let's see if it'll tell us some information about it. This one looks pretty clear. Remember I said most of the standards are NEMA Design B? Let's see what it says right there, NEMA Design B. That's the standard. There's some other information on here that we'll learn about later on, but a NEMA Design B is the most common that you will see by far. If you want a non-NEMA Design B, you're going to have to order it special. So let's see. This one right here is a $25,000 motor for probably a NEMA Design B. But this is totally enclosed fan cool. That's probably a little bit fancier. It needs to be a little bit bigger. It's also hazardous location. I mean, to know about hazardous location. If you're electrical, you have a lot more concern than most other disciplines. If you remember from one of the senior project presentations last week, they talked about using steam for the dryer. Why would they use steam? Yeah, it's kind of hard to make steam catch on fire, right? I mean, people can try, but it doesn't work. But if you use electricity, you can get arcing. And arcing in a paper mill where there's paper fibers flying everywhere, and even if it's wet paper, there's still fibers all over the place, is asking for a fire, in my opinion. So you use steam and water and all that stuff because it's impossible to start a fire with steam and water. It just doesn't work. So over here, you have a totally enclosed fan cool motor that has gaskets on it. That's why these are bolted here. And so no external stuff can get inside the motor. So all of the stuff inside the motor, you don't have to worry about it with natural gas getting in there. Like if you were working in a gas processing facility and you had the possibility of explosive gas getting in there. Or remember the paper mill, you could have fibers, just really fine fibers in the air. And if they get in the windings, they could start a fire potentially. So in applications where you can have potentially explosive materials or fire causing issues, you have to go with these totally enclosed type motors. But you'll also add a lot of cost to this because this is all bolted down in gaskets. Let's see if there's an open drip proof one. So here is, yeah, so look at this one. It's a slightly different machine, but it's $5,000 less, 20% cheaper. And you can see if we click on it, it's hard to tell. Hopefully we can see with the picture in here. Oh, I don't want a car. I just want the image. I guess we can't look at the image of it. I guess we can't zoom in. Well, I guess I can't see it, but you can see on the ones over here, you can actually see that there are slits that are openings into the motor. So airflow can go in. And what that means is this motor can have smaller copper wires. Doesn't need as much copper. So it's going to run cooler because it has that. You can look at these. I mean, this is a different application, but let's go back to the big picture. Let's see. You can see there's no fins on this, right? It's just a metal casing with a bunch of openings for air to go in. We're over here, there are fins everywhere, and that's because you need to reject the heat. You need a bigger surface area. So this motor is actually going to be a bigger motor. It talks about a frame size, but physically these fins are just going to take up more space. But over here, here's a 12,000. This is half the price of this one. Much cheaper, much better for that. All right, questions on this stuff? MATLAB stuff helpful or not? You can say no, it doesn't hurt my feelings.
You said we could do like finding the current, so that, so
Yep.
And show how to solve.
I didn't? Is that what you said?
Yeah, you
Well, that was the first approach that I did, but then the other approach I did in MATLAB was I did the, if you look over here, that's where the Z matrix is. And we did that in class a week ago, I think, when we came up with those loop ones. The advantage to doing that is, you know, right off the bat, what the standard copper losses are, what the rotor copper losses are. You have all that information. So if you need to get more fine tuned in your approach, using this gives you the whole kit and caboodle, tells you everything you need. We're doing the Thevenin approach. You get a lot of the important information, but if you need additional pieces of information, then you can't get there. So I prefer to do this one if you have the enough data, but you know, you can do whatever one you want. I'll post this MATLAB. You won't hurt my feelings.
What's the difference between torque breakdown and slow speed?
Sure. So if I look at this curve and I annotate, this is torque, locked rotor, and this is the breakdown torque. One's the peak and one's the zero one. Because locked rotor means the rotor's not moving, it's locked in position. So there's no speed. Where the breakdown torque is, if you try to exceed that, the motor's going to stop. Just like we saw in lab, right? We tried to tweak it, and then all of a sudden, it just would run at a very low speed. And it should be, I mean, theoretically, if it was possible, it would actually stop, but the torque started to change a little bit. And so that's why with those dynamometers, we weren't able to get it. But if we could maintain a constant torque, the motor would have stopped in place. And then we'd have to shift the breakers off because the motors burn up very quickly when they're running at lock rotor conditions.
The torque, lock rotor means torque no speed.
Torque, no speed. It's locked. It's in zero. It's at zero speed.
How do you get that? Because if there's no speed,
Technically, you don't get torque, but you have to get the thing rotating. So there is some sort of external force. And you can see that here. It's right at the 0 point. But if you remember the MATLAB script file I wrote, look at my slip. I don't start it at 0. What do I start it at? 0.00001, because you can't do the calculations. So you can't really get a torque at 0, but we show that as being the equivalent. It's right basically at almost no speed.
but they're not in the layer yesterday. Thing is supposed to run at small speed.
As low a speed as you can get, which I think most people got 190 RPM.
Okay.
So that would be the equivalent of lock rotor. We couldn't get it down any slower, so that's what we could do in lab.
But then how do you get it slower than that? But you have to.
You'd have to use a different dynamometer. The ones we have, once they start spinning slowly, they don't put out a constant amount of torque. They do a pretty good job at a decent speed, but once the speed starts to slow down, you can't get there from here. So the other way to do it is go and take a, anybody know what a pipe wrench is? Go to Home Depot and get one with like a 30-inch long handle. You put it on the shaft and lean against it, and then hope it doesn't scour the shaft too much, and hope you get the teeth biting in enough of the shaft and lock it in position. I don't want you to do that to the lab equipment. You can try that on your own if you want, but I would appreciate it if you wouldn't do it there. All right. Any other questions? I have a question for you. Exam 3 next week. Who votes for Monday during lab? 1, 2, 1, 2. You giving up, Brandon? All right, let's do this again because I gotta have everybody's hands. All right, if you want lab exam during lab period, it has to be the Monday morning one, because that's technically the synchronous lab one. The other one, it's great if you can attend live, but it's also available asynchronously. So there are people that don't attend it. So most people can make the Monday morning one. So who can do who wants it Monday morning during lab? I need to see a show of hands. Hayden, is that a yes or no? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Other option, who wants it Tuesday during class? Loud and proud. Well, let's do Tuesday. You can vote multiple times. 5. How about Thursday during 6? You said 6, Thursday during class. So the people who voted for Monday, you can vote as many times as you want. Okay, do you want to do that again? Let's do it again because it seems to be confusion. Also in TV land too, if you can actually vote, that would be very helpful. So put your hands up or whatever, except Avery, you can't vote twice. How's that? Because you're logged in, so. All right. Monday during lab. All the way up, let's see, so I can count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Nobody there wants it on Monday. Okay. Tuesday during class, you can vote multiple times. 1, 2, 3, 4, 5, 6. Thursday during class. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I think it's Thursday during class. All right. Thursday during class it is. That's when it's going to be your next exam. So we'll do one more class on Tuesday or Thursday. We'll kind of get most of the material that we need for the exam. And then the following Tuesday, we'll do an exam review. And then Thursday, we'll do the exam during class. So that Monday, we won't have lab to give you a chance to study and prep. Yes, sir. It's open. It's not open?
I saw it, sorry.
Might have been some weird timing or something like that. I remember what I do for the lab submissions. I always try to make sure that I don't make the next lab submission available before the other one is due. The other one's due at 1. And the reason why I do that, is inevitably people will upload stuff at the wrong spot. That might have happened once before. All right, people, have a great day. Talk to you later.
So like 2 hours.